very happy to have Carlos Blanco from Princeton to tell us about dark matter, detection of dark matter. Okay.
Yeah, so thanks for having me here. I'm glad I could make it this time. We had to cancel the last time that I was scheduled to talk, and I apologize, but I'm happy to be here in person this time. And I want to tell you about something that's maybe a little bit different than the way that we usually discuss dark matter direct detection. And since we have like a fairly intimate crowd, just ask me questions in the middle. I would rather not get through everything and have a good discussion with everybody than just like rush through everything. And so, as I'm sure that you've heard in the last 3 talks, dark matter is a thing that we need in the universe, and there's a lot of reasons why we think it exists. And so I will skip that, and I will just tell you about what we know about dark matter and why we know it. And most of what we know about dark matter comes from measurements of the galaxy in a halo, right? So this is a very artistic representation of where we are in our galaxy inside a very large dark matter halo, and it's not to scale, because in reality our galaxy would be quite small in the center of this halo. And measurement of the stars on the galactic disk tell us something, tell us really just 2 very important things about the dark matter in our vicinity. One, it tells us the density, which is about half a proton per cubic centimeter, and it tells us about the rough mean velocity in our neighborhood, which is about 300 kilometers per second. And these 2 things, these 2 constants, tell us something about how we should choose to go after dark matter. It tells us that the number density increases as the dark matter mass decreases. And that means that if we go to lower and lower dark matter masses, we should expect to see higher and higher rates, and so we can make our experiments much smaller. And depending on what mass of dark matter you consider, the detection pathways that you might want to think about change drastically, right? And so let me just point out a couple of signposts along this huge spectra of dark matter masses. The biggest experimental effort so far has been put into these canonical WIMPs that are above about a GeV, and you guys have a great direct detection team here with liquid argon and xenon, and so they focus all of their efforts into trying to detect things above a GeV. Why a GeV? Because it's the mass of the proton, and you can inject energy very efficiently into a nucleus if you're above that mass. Okay? Below that mass, you can still have these quasi-WIMP dark matter models where you have some thermal history that makes sense, but down there you're no longer able to ionize an atom. And so instead of looking for these very rare but energetic tracks in your cryogenic detectors, you're looking for very feeble recoils, and therefore what you're looking for are single quantum transitions, which is in essence very similar to what you think about in optical spectroscopy. And that's much of what I'm going to be talking about today.
Before we skip, so it's not be very silly question, but some of the people hear this. So do we know the distribution of the dark matter as functional energy, or we just don't know? Everybody's certain. We do.
We have a very good guess about the velocity distribution of dark matter.
And what about mass?
No.
So,
We don't know where the dark matter lives anywhere.
so you don't know really. So it's just everybody just look in dark, and
Exactly.
hopefully something happens.
That's right. There are strong theory priors that are placed on this parameter space that tell us that it will likely be somewhere between the sub-GeV and the canonical WIMP picture. There's a lot of theories that place it there, but there's also a lot of theories that place it in this like axion and EV scale boson regime, right?
That's why you said low energy. You know total mass per unit volume.
Yeah.
That's why you say the lighter stuff.
Exactly.
You have a lot more.
Yeah.
Number, right?
Yeah, that's right. That's right.
Can I have a question?
Yeah.
Is there a simple way to understand why 1 GeV is the magical number for ionization of an atom?
We will get there in the next slide.
Okay, great.
So a lot of the clocks that I'll be talking about today kind of look like this cartoon, right, where you have the dark matter mass on the x-axis, and then you have some coupling to the standard model. And the exclusion, the sensitivity of a particular detector setup is what would be in this black shaded region, and there's a couple of features in these plots generally, right? There's a minimum dark matter mass that you're sensitive to, and this is what you're asking about, and that's really just set by the threshold energy necessary to drive a transition. So in the case of xenon, the minimum energy that you need to impart is of order keV,
Right.
And so if you do the kinematics, that means that you need a dark matter mass of about a GeV to drive the transition. That's why that's the magical number. And so if you want to move further to the left to lighter and lighter masses, you need to find systems with smaller and smaller energy transitions. Okay. Similarly, if you want to probe more feeble interactions, that's mostly just dependent on the rate of your backgrounds and the efficiency of your signal, right? And so if you want to get to more and more feebly interacting dark matter candidates, you need very efficient signal generation and a very sensitive detector that you can exclude backgrounds very efficiently. And so that's this list of things that I'll talk about. Small energy thresholds, large signal efficiencies, and low backgrounds. Okay, so let me now say that I'm going to really focus on this EV to sub-GeV dark matter parameter space. And here you have, classically allowed absorption and inelastic scattering off of molecules and nanomaterials. That's really the topic of the talk. Okay, and so the schematic setup here is you have a dark matter particle. I'm going to represent that with chi, and this is not a Feynman diagram. It's just saying that you have that interacting with some initial state psi I. It's going to promote that state, some experimental state to psi f, and it's going to impart some momentum q. And we're totally blind to how it's going to do that. We don't really care. We want to work completely independent of a model. And if you work out the kinematics, if you're looking for an MEV dark matter candidate, you're looking for systems that have order EV transitions, okay? And that they will be able to accept momentum transfers on the order of keV. In the case of a bosonic absorption, you're just looking for vertical transitions of order NeV. And that's why you can go all the way down to an EV if you can absorb the dark matter. Okay, the things that matter for the rate that your detector is going to give you really just fit into this rate calculation, and it doesn't matter what the details of this really are. All of this is to say that the physics really factorizes into three parts. Eta, which tells you about the astrophysics of the problem, tells you about the mean inverse velocity. This is like the phase-space distribution. The particle physics of the problem can be sort of factored out entirely into this thing called a dark matter form factor. And this tells you whether or not you have like a contact interaction or a long-range interaction. This is your vacuum matrix element. You guys can tell us all about that. And then finally, the art of the problem when it comes to bridging the gap between experiment and theory comes in this transition form factor. And that is informed a lot by the condensed matter and the chemistry, and that tells you what the probability is of absorbing momentum Q and doing this transition. Okay, so now let's start with the easiest possible thing that you can go after, which is looking for dark matter using some electronic transition. So here, your dark matter is going to recoil off an electron, it's going to drive a transition, and you're going to look for the de-excitation. And one de-excitation signal that you might look for is a photon, and there, what you're trying to really look at, the kinds of systems that you're looking for are called chromophores. They're small fundamental units that de-excite by emitting photons. And so now let me tell you how we can think about chromophores in the sense of molecules. Okay, so carbon should be everybody's favorite atom. That's a fact. And that's because it makes up everything around you.
Hydrogen. Hydrogen is my favorite atom.
So I disagree. I disagree.
There it is. Sorry, go ahead.
So the electrons in carbon can hybridize into these sp2 and sp3 orbitals, and of importance is this sp2 hybridization, because here you have carbon atoms that are bonded first longitudinally in this single bond, but importantly they form a preferential plane, symmetry plane, and above and below that plane you have these pi bonds, and these are very delocalized orbitals where the electrons are free to drive transitions that the molecule doesn't really know about. The backbone of the molecule stays largely unchanged while the electrons in the pi bond are free to sort of roam around. And if you sort of just close your eyes and you ask, well, should you expect that systems made of carbon are well matched to absorb the momentum of the dark matter at about an MeV? Turns out yes. because the momentum transfer is of order of keV, which is just 1 over the Bohr radius, right? And so that is the characteristic momentum that these electrons are flying around with.
Transfer from where to where?
Sorry?
This transfer is
So-
from which state to which state?
From some pi orbital to another pi orbital.
Ah, okay.
Okay? And you'll see these pi orbitals being signified as these double bonds.
So are you thinking about, you said that this factorizes, but, I mean, don't you need to know, like, in this case here, I would want to know, like, are you imagining that the dark matter has a direct coupling to electrons?
That's
then?
right.
Yeah,
That's
so you are assuming that,
Yeah, so,
and,
so here I'm assuming electron coupling alone. The type of electron coupling I'm allowed to free float, whether or not it's momentum dependent, whether it's spin dependent, it doesn't matter.
and for
That
each
factor.
choice, you would have a different matrix element to compute. in the
Exactly.
Pi organism. So
We-
it doesn't, yeah,
Yeah,
Okay.
we kind of bracket the options between, you know, a contact interaction and a long range interaction. Okay. And so the kinds of experiments we're really thinking about is a system where you have carbon making up small subunits called chromophores, and you're sticking them all in a vat. The vats can be, you know, as big as a liter. The dark matter comes in, it excites a chromophore, that emits a photon, and you're trying to detect that photon. The first problem that you think about is like, well, you know, if you're really just driving excitations, won't the photon just get absorbed? And here, nature has been really quite kind to us, because it turns out that most molecular chromophores have a Stokes shift with relation the absorption and the emission characteristic. So this is like the band where you can absorb energy and the band where you emit energy, which means that the photon emitted from one molecule is likely to just free stream, and that free streaming probability is just proportional to the to 1 minus that overlap. So so here, you know, like this is kind of optimal, you get for free, and the kind of free stream probabilities that we can look at are you know, almost unity, like 65% of all photons created will be able to leave the material.
so what is, it looks like they're kind of, to a first approximation, they're just shifted, the two absorption and emission, so
Yep.
what's responsible for that?
Good. So what occurs is if you think about the selection rules of driving electronic transitions, is if you absorb energy, you also have to excite the molecule. And so what you're really doing is you're driving an electronic transition plus a little bit of a rotovibrational excitation, right? And then that rotovibrational excitation has a lifetime that's like minimal. That totally de-excites immediately. And then when you de-excite the electronic state, you're now working with a much smaller energy. And that, you know, the effective loss due to rotovibrational relaxation is the Stokes.
You're saying you sort of lose the energy quickly, and then you emit the rest of it in momentum, and
That's
so then you're emitting less momentum than you absorb.
Yep.
Okay,
That's right.
got it, thanks.
Okay, so 3 years ago we had a pilot experiment in Chicago where we looked at this molecule paraxylene, which is a commercially available scintillator. And a colleague of ours, Juan Collar at the University of Chicago, knocked on my door and said, look, we got to determine what kind of dark matter we can go after, how dark matter is going to interact with these simple molecules. And so we got to work writing down what like the molecular orbitals look like, what their states do, and how you can absorb momentum through these things. And we found out that it's actually a pretty straightforward calculation, and so we went from theory to actually experimentally deploying this thing. It was quite easy. So this is a picture of the experiment. This is about a paint can's worth of this xylene. And on top of it is a PMT. It's a very sensitive Komatsu PMT. You stick that in a very shielded vat with, you know, your muon vetoes all around. You know, this is ancient lead in the basement of a physics building in Chicago, and you take data. And after about 6 months, we had honest-to-goodness results. And so these are the sensitivities for what was the bleeding edge at the time of silicon and xenon, and then our experiment is this dotted line, right? And this 3.8 hertz, what that corresponds to is that is the limiting background that comes from what the PMT was seeing in its blinded mode. Now this PMT was characterized to go much smaller than that, so we expect that to be mostly driven by cosmic radiation. And so we tried to predict what that rate would be if we'd be able to go to a deep underground location at Fermilab, and we would have the black line if that was the case. And really this is all just to say that fluorescence with these things works, and it's a very cheap, very fast way of probing parameter space. I mean, we were within striking range of Sensei with what's essentially garage level physics. And so, great.
So roughly, sorry, what, you probably said it, but roughly what is the photon, I guess, what do I want to know? I guess I want to know the frequency of the emitted photon. There are single photons emitted in these things?
Yeah, you're looking
Basically,
for.
And so what's the frequency?
I don't know about the frequency, but there are about 5 EV photons.
Okay.
It's UV photon.
Yeah, this is UV
They're
photon.
UV.
This is why we can use a bialkali PMT.
Yeah, okay.
So my question is, if you don't know how the electron interact with the dark matter you're trying to detect, how do you set the detection limit?
Right, so that's
you
why.
can have a plot, but
Yeah.
if the procession is vanishing is small, you're
Right.
not seeing anything.
So that's why this is a function of cross-section. We can rule out cross-sections that are above a set amount.
Oh, this is okay.
Yeah.
Got it.
Okay, so we proved that these fluorescence experiments work and they're very effective. So how do you do better than that? Well, I'll tell you about two options. And the first option is to go after the slower background. And you can do that one of two ways. The first one is to reduce the background in the absorption step. In other words, if you focus on how you're exciting these molecules, you can get some really strong improvements. And so first I need to tell you about how I lied in my first slide. I kind of cheated you because I told you that we were in the middle of the galaxy. We're of course not. We're somewhere off-center, and the galaxy is rotating with respect to the dark matter halo, and this induces an effective dark matter wind. And due to the rotation of the Earth, that's on an axis, this wind can be thought of as coming at some point in the day from the wall and at some point in the day from the ceiling, when you're at a latitude of something like Chicago. And what does that mean? It means that if you have a dark matter detector that can tell the difference between momentum being injected in the direction of your walls and your ceilings, then you can have an excitation probability that is way different than just random thermal noise. And so we went out and we tried to look for chromophores that could tell this difference, and we came up with this simple example. It's called transstilbene. It's very similar to xylene. It's just these two phenyl rings bridged by an ethylene bridge. And they like to stack in these crystals, basically that they look face on all towards the same direction, and they can form these macroscopic single optical quality crystals. They're very inexpensive.
Sorry, can I go back a little bit? Can you maybe just say a little more, just in the first kind of setup that you described?
Sure.
Like, what are the limiting factors? Is it just background?
That's right. That's right.
And it's just like low frequency, well, just like photons or
Yeah,
what? Like,
so
what
it's-
is the dominant?
You count the clicks coming off of this PMT,
Yeah.
and you say, what's the dark matter interaction have to be to give you a signal that is higher than what I pick up as the dark rate of my PMT? That dark rate of the PMT was measured here, but it's calibrated at deep underground locations to be here, so that would be the ultimate sensitivity. Can you do better than that? Can you beat the dark rate of a photodetector? Yes.
So is that the dark line then? Is that essentially zero background, or is there some? If you could reduce the background to literally zero, would there still be some other thing like, I don't know, like just electronics noise or in the PMT or something? I mean, what would be?
Yeah. So
Is that pretty close to the zero background limit? The black
No.
line?
No. The zero background limit is many orders of magnitude below this. This is a very dirty experiment, what I'm showing here. This is the background coming from a PMT that's really calibrated to do physics at ionization energies, not at fluorescence energies. And so if you were to be able to dip this background way further down with the lowest noise photodetector, which turns out to be Sensei. Sensei is a photodetector that's essentially background free. Then you can go lower and lower, and then your main source of background is essentially the thermal self-activation noise and the very, very tail end of beta decay of carbon.
And now experimental question. So you can in principle cool the detector
That's right.
to control thermal part of it.
Yeah.
But now this background is mainly from actual events that strike the cathodes, or some other particles, just striking cathode. There's nothing you can do. But there's no way you can shield them. They just simply come to the detector. They're rare, but they're there.
That's right.
Or it's thermal. It's not thermal, I guess, right?
Yeah. So this background rate up
Uh-huh.
here, we think is coming from things hitting the cathode.
Real deal, real particle hitting
Real
the
particles
cathode,
hitting the
right?
cathode that weren't vetoed by the paddles.
So cooling is because they look exactly the same as
That's right.
your events, right?
Yeah.
And nothing to do with temperature, not sort of. Right?
That's right. That's right. This is what the background is known to be if you can totally shield the astrophysics of the problem. If you can get rid of all the cosmic rays, that's the dark rate limit of a bialkali PMT.
And you're not doing that in the dotted line yet.
That's right.
That's what but I think that's what I sort of meant by background free. I mean, you've got the PMT that you have, you don't get to turn off that background, but
That's
you're putting it into a background free environment.
I see.
You're saying that's essentially what that
Yeah.
dark line is.
With this experimental setup, the best you can do is the black line.
Oh, okay, I
It's
got
all
it.
solid.
I got it.
Okay.
So, sorry, so the reason I was asking is because, what I was sort of expecting to hear is that, okay, so we made this paint can with the thing, duct tape on top, the photomultiplier tube duct tape on top, but now we're going to make one that's bigger and it's going to go in deep underground. You're just going to make it better, make it bigger, whatever, but you're not talking about that. You're saying, okay, we're going into direct detection.
Yeah.
And why is that? Is it because you can't compete with Sensei, or?
No, so we're going in a different direction because there are smarter ways to gain sensitivity than just making your vat bigger and trying to look for lower rate PMTs, right? So trying to find more and more sensitive PMTs forces you into instrumenting smaller and smaller areas. And then it becomes totally prohibitive to instrument, a ton scale detector. So that's a non-starter.
Okay.
So you want to get a little bit more clever, and that's why you want to reduce the background rather than reducing it in the fundamental noise rate, lowering it in the way that the signal comes out. Okay? And that's why we're looking at the daily modulation. And if you look at the rate probability, at the expected rate as a function of time, looking for this daily modulation, you get curves that look like this. And so here, every curve corresponds to a different dark matter mass, possible dark matter mass, throughout the day for a crystal that's the same size as the paint can. And throughout the day, you see that the signal that you're looking for really varies by quite a lot, up to 70%. And that's a very verifiable signal. That looks a lot different than just a constant dark rate. And that allows you to, get rid of a lot of background.
So this is the overall rate. This is not some directional thing.
This is the overall rate, right? So this crystal will absorb preferentially in one direction, but emit isotropically.
Okay, but it is a directional effect because
Yes.
it's the crystal has a preferred direction.
That's right.
Relative to
That's right.
Okay.
So we know that the dark matter has some amount of just velocity that we think is thermal.
Yep.
So as we're flowing through it, how are we sure that how does our speed moving through the galaxy compare to the speed of the random motions of the dark matter?
Good. So it turns out that the way that we build the standard halo model, as it's called, is you just think of Maxwell-Boltzmann distribution of dark matter velocities in the rest frame of the galaxy, and then you do a Galilean transformation into the rotational frame
Right.
of your solar system, and the mean velocity of the dark matter sort of in its own rest frame is about 50 to 100 kilometers per second, and you're rotating around the galaxy at 60 kilometers per second. So it's an order 1 effect. you still get things coming from all directions, so your rate never drops to 0,
Got it.
but you do vary it throughout the day.
Okay, so
This is something that we take into account. This is a full simulation of the velocity distribution. It's not just asking, how you change if all of it comes from here or all of it comes from here.
okay, neat.
And this shouldn't be surprising because what we've done is we've selected a target where this transition form factor is anisotropic. And so we should expect that the rate is anisotropic. That's what drives this. Here you were asking about this object, right? The velocity distribution. We've modeled that fully in these simulations. And so what does this buy you? Well, say you had a crystal and you totally ignored daily modulation, right? Say you were just looking at the paint can and trying to do cuts based on rates. Well, there, for a 1 kilogram crystal, you would have sensitivity at these dashed lines. In looking for your daily modulation, you essentially get sensitivity improvements by 2 orders of magnitude. Okay? So that's this black line. And not only that, since it's a verifiable signal, there you have an actual discovery potential, not just an exclusion sensitivity. And so that's great. And these projections are for background rates from background rates of the PMT or your photodetector that are very much pedestrian. Like these are not futuristic. These are, something like a 1 per minute dark rate. Okay.
So what kind of a scale of an experiment is this? Is this like a paint can scale, or is it much larger?
1 kilogram is about this big.
Wow.
Yeah.
Okay.
And you might ask, is that going to be expensive? No, you can probably find a kilogram of still being within 2 blocks of this place. This is found in every undergrad laboratory.
So the graph you showed earlier in the previous one, is experiment or simulation?
This is simulation,
This is simulation.
and based on this simulation, we predicted this sensitivity. Okay. Now these blue lines, these blue lines here are benchmark dark matter models that would give us the right relic abundance and that have a self-consistent thermal history in the early universe. And so that's where we expect dark matter to be. And so it's pretty surprising that with just 1 kilogram of still beam, you can already probe something like a freeze-in scenario over 2 orders of magnitude. And you start to probe this scalar freeze-out scenario at, with a kilogram. And so this got quite a bit of attention, and it's now being developed at Fermilab. They're characterizing the materials actually here in California, and then they're going to be flown to Fermilab where they're going to be deployed. So we're quite excited about that. What happens if now you want to look for not just the electron coupling, but say you want to go after dark matter models that couple instead to baryons? Then you're looking for nuclear recoil, and you can do the same tricks, right? You can say, how do I excite electrons using nuclear recoil, and how do I look for the photon signal that you get from that? Well, let's think about how we do that with atoms, right? So you can ionize an atom by recoiling off the nucleus, and the way that you do that is the dark matter comes in, it recoils off the nucleus, and from the point of view of the nucleus, now all of your electrons have picked up a phase and are no longer in the ground state. And so you can just calculate the probability of them being ionized. And this is what dark matter experimentalists called the Migdal effect. And this has allowed people like the xenon collaboration or the liquid argon community to take their sensitivities that stop at 1 GeV and go towards lower masses, looking for this inelastic second order process. And so this has, really revolutionized the way that we look for light dark matter with these noble gas vats. And so a natural thing is, well, do molecules have a Migdal effect? And as we discovered last year, yes, they do have a Migdal effect. Not only do they have one, they actually have 2. And the way to understand this is that if I have the most basic molecule that you can form, which is just 2 atoms, how do you shift the nuclei? Well, you can decompose all of their motion into a center of mass motion, where they move together, and a relative motion. And each one of those 2 things come with their own separate probability of excitation of the electrons, right? And so the center of mass one is totally morally equivalent to the atomic Migdal effect, whereas this relative motion one is something totally new that only exists in these scintillators. And that's the non-adiabatic coupling Migdal effect. And so this comes from effects beyond the Born-Oppenheimer approximation. Importantly, because these internal deformations don't have to move the entire molecule, they don't pay the same kinematic penalty as the center of mass recoil effect. And so they're expected to dominate across all dark matter masses. And when we put this all together and we turn the crank, we find that that's totally true. So for two toy examples of carbon monoxide and nitrogen, which you would never actually use in an experiment, they're just things that we can calculate almost exactly. We find that the sensitivity coming from the non-adiabatic coupling effect totally dominates the center of mass recoil. And we also find, quite interestingly, that even for these very dumb molecules, we're already within less than a factor of 2 from the equivalent silicon sensitivity, right? So these are sort of the bleeding edge experiments now. And the silicon sensitivity comes from a calculation of a Migdal effect that only takes into account center of mass motions. And so a natural thing to ask is, does a non-adiabatic coupling effect exist in silicon? And if it does, then the community should, calculate it, because then this line should be expected to actually be down here. And the silicon community can enjoy way higher sensitivity that way. The other thing that one can ask is, well, how do you go about finding really optimal molecules? And so I'll get to that. Another thing that you get for free is that the molecular Migdal effect is also directional, because molecules aren't isotropic, and so you can make these similar daily modulation curves, and you'll notice something kind of subtle here. As a function of dark matter mass, the phase of the oscillation changes. And so in these experiments, you can tell the difference, and I believe it's the only kind of experiment that you can really do this, is you can tell the difference between a light dark matter particle that's strongly coupled versus a heavy dark matter particle that's lightly coupled. This was very surprising to us. It's a very subtle effect that comes from the fact that there's two probabilities that factorize from the nuclear matrix element and the electronic matrix element, but we were quite excited about this. So how do you go about finding molecules that are optimal for this? Well, it turns out you can actually observe the non-adiabatic coupling effect in real life with spectroscopy experiments. So this is a molecule called toluene, and the first electronic transition of toluene is classically forbidden because this thing has no dipole moment. And so you go out and you measure the electronic transitions, and you find, well, it's actually there, it's visible, it's quite visible. Why is it there? That's classically forbidden. Well, it's there because the vibrations of the molecule drive a non-equilibrium dipole moment. And it turns out that the matrix element that dominates this kind of forbidden transition is the same matrix element that is responsible for the non-adiabatic Migdal effect. And so, whereas in the atomic case the Migdal effect has never been measured, in molecules it's essentially been measured since the 50s. So that was really exciting for us, because it means that we can do some quite interesting data mining to look for really just the best possible detectors for dark matter. And there you run into a really complicated roadblock, which is the intractability of molecular space. So the question you can ask yourself is, how many molecules can I make with just these basic atoms? If you have 9 atoms, you can make hundreds of thousands of them, and that's kind of computable. You can do density functional theory on this many molecules, and it'll take a ridiculously long time, but you could do it, at least in principle. But when you go up to 30 atoms, you're now totally intractable. There's not enough computational power in the world currently to do this. And for comparison, this trans-stilbene molecule that we've selected as just the simplest candidate already has 26 atoms. So looking for optimal molecules by computing each one from scratch, totally intractable. So what do we need to do? Well, we need to look for favorable properties. That's called cheminformatics, and that exists as a field. But we also need to interpolate from existing computations into new molecules. And for that, machine learning is optimally suited. And so that's what we're doing now.
So optimal in terms of what?
The best molecule to make a dark matter detector. So to maximize the sensitivity to the dark matter.
Maximize, you're not maximizing cross section. You maximize the sensitivity. Where do you get the sensitivity?
So the sensitivity, that just means maximize the rate of the signal with respect to the rate of the noise. So that means maximizing the non-adiabatic coupling matrix element, maximizing directionality. All of these things need to be.
But
But for a given, you assume a cross-section of the dark
Right,
matter
that's a
to
fixed
the
point.
electron.
Yeah, that's a fixed.
And then that's some number that you will vary, but for a given value of that, you want to know how big of a signal you have.
Yeah,
But you can only do that.
So you
Oh,
don't,
you want to
you don't,
see.
it's a prefactor, right?
Yeah.
You don't know this
So you want to be able
prefactor.
to, after interaction, how much you can get into excited states,
exactly.
then how much will turn into a photon. So that it's the latter two states you're interested in.
So we're basically optimizing this
Alright.
matrix element.
Right.
This matrix element and all the other electron matrix elements that we consider for scattering.
It's like an
and-
efficiency, right?
Okay.
How do we do that with machine learning? Well, let's start with a small data set, a data set called QM9, which is quasi-complete. This was like a huge effort. It's essentially like the Human Genome Project, but for molecules. And they tabulated all possible molecules that are experimentally viable up to 9 atoms, and they computed a bunch of DFT on them. And so we can use that as a training set. And to validate a machine learning network that we made bespoke for this task. And then we can say, okay, take that network and now apply it to a sparse data set that has much more atoms per molecule, and then use essentially a fancy interpolator, which is what machine learning is, to really complete the data space. And so this is a plot that's kind of hot off the presses. And what it's showing you is, as a function of essentially an order parameter in our network, this is a generative network, what we do is we put in a data set, a subset of QM9, right? And that's the red. And we ask, generate a bunch of molecules. And so as a function of this order parameter, we generate essentially all the data set and only from that subset. And as we increase it, we start generating far less of what we trained on and far more new molecules and far more molecules that belong to the rest of QM9. Now, new molecules here really just says molecules that are not experimentally viable. And the fact that the machine can tell the difference between these three populations means that it's really learning chemistry. It's pretty beautiful.
So you basically predict, let's give 30 atoms, and you're going to try to find some arrangements. The thermally stable.
Yeah.
And they actually can be made, or who knows, right?
That's right.
But that's actually, it's quite like, I think in medicine, they still have very limited parameter space to do drug discovery, right? But here,
That's right.
it's a tricky business. So if
It's very tricky.
You can say you can make a molecule like that, but it's, in reality, you won't be able to make it, right?
Yeah, so all the molecules that are known to not be, that you can't make are in blue. The ones that you can make are in these other two populations. And it's funny that you bring up drug discovery, because this research is the only dark matter project that I can think of that's funded by the NIH.
You've got done high throughput screening work.
That's right.
And you screen tens of thousands of molecules in one shot. So here you're basically doing similar things.
Exactly, and that's why we use very similar machinery.
So I'm sorry, I don't understand this plot. So the deviation is what is your training sample, right? As you go to the right, you're using less and less training data, which is the red.
Not quite. So
No,
you can
okay,
think
I
about this as a
understand.
knob that allows your black box to either generate things that are very close to the training set, or can explore a latent space farther and farther away from that initial training location. And as it's able to diffuse out and to deviate from its original location, it's able to produce new molecules, and molecules that belong to a set that you know of, but that is a superset of your training set. And so that basically means that it's learning the manifold where molecules live.
But it knows it knows the difference between the blue and the green, or the blue and the green you only know because of truth data.
Well, we know the truth data between the blue and the green, but
Yeah.
we trained the machine to also tell the difference, right? So
That's-
blue are all molecules that are not found in QM9 because they are not experimentally viable. And so part of our network is a
Oh,
subroutine
oh,
that is able to tell the difference between
okay.
the submanifold that is possible and whatever
Oh,
else.
I see.
Yeah. Okay, so this is really interesting. Stay tuned for this. In the next few months, we'll put this out. Okay. I only have a little bit of time, so hopefully I'll be able to tell you about this next part, which is how do we reduce backgrounds beyond that? Well, now we can focus on the emission study, right? And one way to do that is to look at nanomaterials. So I will just tell you that there are these things that are called quantum dots, and they can give you signals that have very interesting statistics that are far different than random statistics. Okay, so what is a quantum dot? This is a computer-generated graphic of a lead sulfide quantum dot. Is a nanoscopic crystal, and on its surface you have these molecules that are just there to stabilize the crystal from falling apart. And energetically, what is happening can be understood by first considering an infinite crystal. So let's consider an infinite crystal here. The electrons here live in block states, which are just a block piece that tells you about the microphysics and the symmetries in the lattice, times a free plane wave, right? The solutions of the Schrödinger equation in free space. As you imagine taking these boundary conditions from infinity and shrinking them to the size of the wavelength of an electron, your states now look different. The microstates stay, the microphysics stay the same, so the block piece remains relatively unchanged, but now your free space wave is now no longer a solution, and that piece really turns into what's called an envelope, a bound envelope. And that's sort of the first order understanding of what the electronic states look like in these quantum dots. And energetically what that looks like is where you would start in the infinite crystal having some continuous valence and induction bands. The act of quantum confinement allows you to resolve the band edge states that really look like particle in the box. Okay? And it's interesting because the radius, the characteristic size of your crystal, controls your effective band gap. So you have an extra knob that you can use to tune the electronic properties. What's more is you get this interesting effect that occurs when you excite an electron from your valence band deep into your conduction band, creating what's called a hot carrier. These things can relax down by a couple of ways. One is they can emit a bunch of phonons, but now you're living in a nanocrystal, and your phonon density of states is very different. And so that process turns out not to be very efficient, and instead you relax this hot carrier by generating more excitons that now live on these band edge states. And because you have multiple band edge excitons, they can then recombine the electrons in the holes and give off photons that are correlated in time to within the radiative lifetime of your exciton. Okay, so what does this mean practically? What this means practically is you have these chromophores called quantum dots. You put them in a vat that looks the same paint can, but instead of having one PMT, you have two PMTs. And instead of looking for single photon counts, you look for correlated double photon strengths. Thermal noise has a very, very hard time mimicking that, it turns out. And so you can reduce background very efficiently this way. And so these are projections of what those sensitivities will look like for two different scales of deployment. So here you have a 10 gram month exposure of quantum dots. This is like a 1 liter volume of quantum dots suspended in liquid. And at that scale, this sensitivity is kind of independent of the dark rate of your photodetector, if the rate is of order 1 hertz. So even with these like off-the-shelf parts, you can already characterize these perfectly because these are essentially background free at this scale. So you build this experiment, you characterize it, you're essentially background free, you can do it. And then you scale it up by a factor of 10, and then you can start telling the difference between background. And this ability to do this double counting thing allows you to go from here all the way down to here. So this is this order of magnitude improvement that I was talking about before. And this is all existing technology. This is just a clever way of going after these signals. And so people were quite interested in this. Also because there exists honest-to-goodness data that you can look at to do sensitivity studies of, say, light, dark matter, bosonic absorption, right? So you'll see that these sensitivity curves are jagged, and that's because this comes from honest-to-goodness data. This is like a pre-calibrated experiment, if you want to think about it that way. for absorbing something like a dark photon. Some very good experimentalists in Stockholm got very interested in this, and so we wrote a letter of intent and are starting a collaboration called the Quadra Collaboration to actually deploy a quantum dot-based detector. At the same time, there's an MIT team that is also trying to deploy this, led by Lindley Winslow, and this is a CAD rendering of what that might look like in sort of its fully upscaled state. And so these are sort of next generation PMTs that are being developed for the Xenon collaboration that we're going to be able to use afterwards. And it's going to be deployed in two phases, an intermediate phase, which is this like totally background free phase where we characterize, and then we deploy it 3 years later, and the expectation is that we'll outdo pretty much everything in the field for sub-GeV dark matter. Okay, can you bring these things together? Can you do the selective excitation and the selective emission? Can you bring them together in such a way to get multiplicative background reduction? I think yes. So this is something that I'm working on right now, and this would be the, the next stage in this research program would be to form these hybrid type detectors, where you have this directional absorption followed by a charge transfer and a radiative recombination in time coincident photons. And if this is possible, and there are very good reasons to think that it's possible, the multiplicative effects are kind of ridiculous. So these plots, what they show are the individual sensitivities of a 1 kilogram detector of quantum dots and a 1 kilogram detector of trans-still beam in the dark red and dark black. Okay, individually, that's how good they do. They do better than everything else in the field, but they're still within reach. If you put them together and you get a multiplicative effect, you're now doing better by many orders of magnitude. You'll be able to rule out freeze in and freeze out in the sub-GeV parameter space entirely. Why do we expect this to be the case? Because there's experimental data to show that this charge transfer happens. It turns out that the same process that governs this dark matter detection scheme is the same kind of processes that the private sector has been really interested in, because they will break the Shockley limit of photo absorption. So this is essentially like it would be the best type of solar harvester, but instead of having to be very clean and marketable, we can make it large and not very sensitive to the sun, but extremely sensitive to dark matter. Okay, I think I have 5 more minutes. I'll tell you about going beyond direct detection with these techniques. So I've mostly just told you about what happens if you stare long enough at chromophores in laboratories. And these chromophores are just batches of molecules. But it turns out you can do this in space to do what's called indirect detection of dark matter. And there, what you're really looking for is large astrophysical volumes of molecules. And instead of photodetectors, in bialkali PMTs, you use telescopes. And these things exist. They're called molecular clouds, cold molecular clouds. This is an example. This is the Barnard molecular cloud. And it looks like there's something wrong with the telescope.
Is the cloud a black thing or this thing around it?
It is the black thing, right? So here's what's happening. The cloud is composed of hydrogen. It's very dense hydrogen by astrophysical standards, very diffuse by Earth standards. It's about hundreds of atoms per cubic centimeter, but this hydrogen basically absorbs all of the light above the necessary energy to drive its transitions, and all of that light is really just absorbed at the surface. You can kind of see the surface skin depth there, and so inside at the core of these molecular clouds, you have an incredibly clean laboratory where the ionization rate is just governed by cosmic rays. And we know quite a bit about cosmic rays, and we know quite a bit about how they ionize hydrogen, and how that ionized hydrogen really controls the chemistry of these clouds, and therefore the spectroscopy. And so we know very precisely, to astrophysical standards, what the ionization rate is. If dark matter also interacts with these clouds, it will contribute to the ionization rate in a visible way. And we can use that to set constraints on dark matter that interacts very strongly with the standard model. So what do I mean by strongly? Take a look now at the scales that I'm talking about here. So this is like the electron cross-section. The experiments that I was talking about before, these very sensitive experiments looking for feebly interacting dark matter, really take place 10 orders of magnitude further down here. Okay. Now I'm talking about very strongly interacting subcomponents. And in these scenarios, what happens is that the dark matter tries to get into your laboratory, but it just can't. You get stopped by the atmosphere, you get stopped by the walls, by the concrete, by your neutron panels. You're totally blind to it. And so direct detection experiments on Earth have an overburden limit that's really set here. If you set up a balloon experiment and you send it up to near space, you do a little bit better, and satellite experiments do a little bit better, but it turns out that there's still this open window here that is kind of fundamentally unprobable by current experiments. And normally, that kind of strongly interacting dark matter would be totally ruled out by CMB considerations, but it turns out that if the strongly interacting component of the dark matter only constitutes a small fraction of it, and models that have strongly coupled components predict that it will only be a small fraction of it, in these scenarios, the CMB loses sensitivity entirely. So what do? We look at molecular clouds, and it turns out molecular clouds are sensitive to exactly this open parameter space, and we can look at things in both orthogonal couplings, the electron coupling and the proton coupling. And so in the electron case, which was the first study that we did, the open window is this sort of white space up here, and molecular clouds totally rule it out. We were quite happy to basically see an open window, write down the basic chemistry, and completely rule it out. And then it became obvious to us, like, let's just apply the molecular Migdal effect and see what the sensitivity is for the nuclear recoil case. And that's what the right-hand side is. It turns out there it's much harder to constrain dark matter, but overwhelmingly the biggest constraint in these strongly coupled subcomponents is this Migdal effect in space paper. And so this is adding to the many reasons why looking at chromophores, looking at chemistry, looking at nanomaterials can really benefit, HEP departments everywhere. Right? These are all techniques that have existed for a very long time, all technologies that are well understood, that we just really need to reach out across the hall and call in, our chemist friends or condensed matter friends and tell them, look, teach us. Okay. I think that is it. Let me just conclude there and take questions.
Thank you.
So, how pure does a sample need to be? Like, experimentally, there's always an impurity, even though you're synthesizing some molecules, right?
Yeah.
Is that a big problem?
Yeah, so in the chemistry lab, if I have a dirty sample and I want to clean it up, one of the best ways to do that is to crystallize it. We're working with crystals.
But like how?
If you form good crystals, they are inherently extremely pure because impurities lead to bad crystals. The crystal formation does not propagate. And so the problem of purity when it comes to molecular crystal really boils down to the problem of large-scale crystallization techniques. And that has been really perfected for many years. That picture of a crystal that I showed you is a single crystal. It has no defects.
But
But does it matter if it's a very good crystal? Seriously.
Well, you can work with
when
that.
in fact its defect can contribute to your signal. If you don't care, right?
You might care. So
Yeah.
what we're learning is that very sensitive experiments do care about microfractures in crystals because these small atomic shifts lead to phononic excitations and energy depositions as these crystalline phases rub against one another. They look like energy deposition. And so if you're looking for small energy depositions, these fracture points can lead to backgrounds. And so you might still be able to work with things that have fractures and that have defects. It's always better to reduce them.
how do you physically introduce signal in these cracks and defect? I don't see it because let's say you cool the whole thing down, nothing comes to the crystal. What contribute to?
Yeah.
Why do they produce 5 EV photon? There's no chance they produce a 5 EV photon.
Yeah, so
right?
the experiments that see the backgrounds from these things are not looking for 5 EV photons, they're looking for like milli EV excitations. So you're right, the signal is different. But the point remains that say I have a single atomic dislocation, right? What I have is a color center, which is another kind of chromophore, right? That's going to change my emission characteristics, right? Like the fact remains that you always want to work with the purest possible crystal. If you introduce color centers, if you introduce dislocations, you need to be able to characterize those backgrounds. And so it's
So the only source of excitation is the dark matter. You are happy if they actually produce more signal, right? That's why
Yeah.
you do this weird synthesis of all these weird molecules. Right? You want to find molecule.
Yeah.
Have a weird combination structure to give the highest efficiency.
mhm.
Once the electron, one of the Migdal effect already taking place, then they give the hardest.
But Shangdong, I think the thing is that, right, the expected result is that you're not gonna find any signal, right?
Yeah.
And then to interpret that result, you have to know what your sensitivity is. So,
This
it's-
crowd,
isn't it-
but this
is that
crowd will
correct?
not
I mean,
produce
so it's kind of-
anything. This
it's a
crowd-
question, no, but I mean, it's a question of, you know, in order to know what your result means, you need to be able to theoretically characterize the response. So if you had your cracks,
A crack,
you were
yeah.
able to completely theoretically characterize it,
No,
you'd be right. Is that correct? Or-
Yeah. So calibration is hugely important, and if you just look experimentally at, you generate 10 crystals and you do spectroscopy on the 10 crystals, the spectroscopic analysis will be slightly different on the 10 crystals, right? The quantum efficiency is going to be different. The emission characteristics are going to be slightly different, right? And that all comes from fundamental impurities and cracks inside the material. A crack is not only a place that you can have dislocations, but it's also a reflection surface, which means that you can trap photons inside there. Their free streaming is going to change.
But they have to be very, very dirty, crappy crystal to give you
Yeah.
that kind of effect, right? You're
Well-
really looking for extremely weak events, so weak. These, you got to be very piece of extremely dirty
So then
crystal, right?
Then I don't
It's
think
so
I'm
sad.
understanding your point. Are you saying that the difference between no cracks and a few cracks isn't the difference?
I would expect very little effect because if the 99.99% of your material is your crystal, the rest is just a defect, whether it's in sheet form, line form, or point form. They produce you are looking at extremely weak events.
Yeah.
Extremely weak events. We're not talking about.
So I think we're talking about different kinds of crystal dirtiness, right? Like I'm talking about the difference between something like the kind of quartz you find in rocks that is essentially opaque, that looks white, versus a totally translucent optical quality crystal.
So why it's terrible, of course. Yeah,
But
you need
This is possible with molecules.
But they change the optical, changing how light may come out of the crystal.
I mean,
So you
Shangdong,
really don't need
are
to
you
verify
saying
particles.
that it's pretty easy to get things clean enough?
Of
I'm not
course.
sure if you guys
Of
are
course.
really even disagreeing.
I'm not sure we
I
are.
think,
It's very easy to make a reasonably transparent crystal. Right?
Yeah, I agree.
That's what I mean.
yeah, I think
You
maybe
can't
you
get
guys
it
are
either
saying
way.
the same thing. I mean, you don't need it to be perfect, but you need it to be,
Quite good.
yeah, I can't tell, but.
And,
Yeah, no, I don't think we're disagreeing on this.
and for a similar thing, when it comes to a Migdal effect, the isotopes will do something, right? If you have different isotopes, even though the crystal is perfect.
Yeah. Are you worried about like radioactive decay?
No, just like if I have different isotope, the mass of the nucleus is different, and the response will be different, and is that a big problem?
Isotopic effects are really quite small in carbon. So if you're looking at just hydrocarbons, which are the kinds of things that we're looking at, the isotope contamination can be quite low, especially if you start with petrochemicals that come from deep underground wells to begin with. That's very low radio background, and that's essentially all the same isotope. So you can really limit that. Now, if you were worried about the radio background, because that does deposit a good amount of energy, there, I think, you may have a little bit of a point, but there is a clever way to get rid of that, because you basically say anytime that your detector lights up with a decay, you just ignore that. You're not looking for your detector to light up, you're looking for single photon events or coincident photon events. And so you can get rid of decays that way.
This is a much more general dark matter question, but do we have reasons to believe that there are lower bounds of some of the electron interaction cross sections we were looking at?
Lower bounds.
Like you had some lines in there about like freeze in or freeze out.
Mm-hmm.
Those are things I've heard in the seminar once, but cannot remember anything about. Like, could the cross section like just be 0, or
Could it just be, yeah.
okay?
You can live in a dark matter nightmare scenario where you're only coupling to the standard model view of gravitational interactions, and then you're totally screwed, right?
Mm-hmm.
But let me ask you, what predictive dark matter models can you really write down that are consistent with early universe cosmology, that are consistent with structure formation? Most of them have at least feeble couplings to the standard model.
Got it. Okay.
And all of the good dark matter candidates that we have generally have some prediction of what the cross-section ought to be.
So from cosmology simulations, does that suggest we need a coupling at least this week?
It depends on what dark matter model you're talking about. Right? So,
I mean, just very generally, I would just say that, you know, if you just had gravitational interactions, there's no way to understand how you get the relic abundance in the first place, right? So in other words, the fact that there's a relic abundance somehow suggests that this is a very hand-wavy argument, but that there's some additional interaction that's non-gravitational, that's responsible for its presence in the universe, okay? It's relic abundance.
Yeah.
Now, there's not a way to make a direct line between that unless, as Carlos says, like there's a lot of models and you can see it very frequently. You do have some sort of signal that...
So like if dark matter got made at the Big Bang, it has to couple somehow from whatever that creation
Yeah, if
process
you just had
was.
something with just gravitational interactions that was produced early on, there wouldn't be anything left today. Right?
you need a way to either populate the dark sector or to deplete it. And the fact that, you know, the density ratios are like, 1 to 20. No, sorry.
1